All right, we are picking up on slide 25 of the chapter 14, part 1 PowerPoint. We're almost done with this one. So we did the first order problems. Now we're going to go into second order type problems. So if you have a reaction where they tell you that it is second order and one reactant, or if you see the rate law and it is the rate equals K times the reactant squared, it is implied that it's second order there, then we're going to go through the same steps where we have to think about, okay, in that equation, the units of K change based on the overall order. So it's just something you have to kind of work a few problems and get used to it, but we know the rate is always in molar per second or molar per minute. The concentration is in molarity, and if we square it, so on the right side we have molarity squared, on the left side we have molar per second. If we divide the concentration units over, it should help us isolate what the units of K should be. In this case, if you work with it, the unit should be 1 over molar times seconds, both in the bottom, or liters per mole times seconds in the bottom. Either way, but you need to get used to that because whenever you do a problem, if you're solving for K, you are expected to know what the units are going to be. Okay. For second order, we also have an equation if we're solving for how much of a sample remains after a certain amount of time, or how long it takes a reaction to go from one concentration to another. For this one, we only have one equation to use. It's shown on the slide. This one is also on the formula sheet. So on the test, if you see the reaction is second order and you're going to do some math problem with it, that's the equation you're going to use. When we look at the graphs, specifically, this slide only shows 2 graphs, but technically there are going to be 3 that we're going to make. We're always going to make the concentration versus time graph initially. That's usually going to come out to be curved. If we take the natural log of the concentration, if it's first order, that will make it a linear graph. Okay, so let's look at this one. If I take some data from an experiment, if I do the natural log of the concentration versus time, if that was a linear graph, then it would prove that it's first order because it proves the exponential relationship. In this case, it does have a little bit of a curve to it. If I did a linear fit, I would see the R squared value is not close to 1, and I would also, R squared value measure is the correlation coefficient. It measures how closely the data fits a line. So since I have a curve here, the correlation coefficient would not be ideal, which is close to a value of 1. So I can tell it's not linear, but then for a second order reaction, if I do the inverse of the concentration, 1 over the concentration, and then graph that value on my y-axis, then I actually see that this one does come out to be linear, and that is going to be the graph that we make to prove that a experiment or a reaction is actually second order. Okay, so we got the natural log graph, we got the 1 over concentration graph for first order and second order. All right, now I'll finish that where when we get to 0 order, then we're going to have a case where the concentration versus time graph is linear. So again, there's 3 total graphs. Which one's linear will determine what the order is for us. Again, we'll see that in a few minutes. But before we move on from second order, let's do one more problem. So decomposition of HI is a second order reaction. There's no way you know that unless they told you. Okay, so they're specifying it's a second order reaction. That tells you that the equations you're going to use have to be the second order equations. Once we know that though, then we can just get the information. So how much time is required for the concentration of HI to go from the initial amount of 0.01 molar to the final amount of 0.005 molar. Okay, and they gave me the value of K, which is 31 over molar times second. So actually I worked this on the board already. So if you can see that, I plugged in the numbers that were given. 1 over AT minus 1 over A0 equals KT. So I plugged all the numbers in. If you do the math there and solve for it, you should get a time of 3.3 seconds. All right, now we're moving on. Zero order reactions. So what is a zero order reaction? That would be a reaction where the concentration of the reactant has no effect on the rate of the reaction at all. Okay? Now that seems weird because normally for a reaction to happen, there has to be, like, your reacting molecules collide with each other. The more collisions you have, the more reactions you have. So it seems like increasing the concentration of the reactant should always speed the reaction up. Okay? But there are cases where that doesn't happen. Specifically, a reaction that is regulated by enzymes. So, example, if you drink alcohol, if any person drinks alcohol, everybody always hears the saying that your body can process about one drink of, like, the alcohol that's in one alcoholic beverage. So your body can process one drink per hour. So if I drink 2 beers, there's a certain amount of alcohol in there that it'll take my body about 2 hours to process it all. The enzyme that starts that process is called alcohol dehydrogenase. I have a certain amount of alcohol dehydrogenase in my body, in my liver, I guess. So when I drink alcohol, all the enzymes I have in my body start working to break that alcohol down. If I drink another beer, my body can't process it any faster once all the enzyme is working as hard as it can. So even though the concentration of alcohol in my blood and my kidneys, or excuse me, my liver, even though I increase that concentration, it doesn't speed the reaction up at all because the enzyme is already maxed out and that's all it can do. Okay? So what we see with the zero order reaction, I'll go ahead and talk about the graphs first, is that the rate of reaction is constant. Okay? So if I graph concentration versus time, previously for zero order and, excuse me, for first order and second order, both graphs would have been curved. One of them was an exponential graph, one of them was an inverse graph, but they both end up giving a curved decline. For zero order, the reactant is being used up at a constant rate. So basically, I get a linear graph where, again, if I drink alcohol, my enzymes start working as fast as they can. They work steadily until all the alcohol is gone, and then the reaction stops. Okay, so that's what the graph of a zero-order reaction looks like. Now, since that one's linear, we don't even need to make the natural log or the 1/over concentration versus graphs that we talked about before. But if we are doing a reaction and we don't know, is it zero order, is it first order, or is it second order, if we make all 3 graphs, only one graph will be linear, and which one it is will tell me what the order is. If the concentration versus time graph is linear, I know it's zero order. If the natural log concentration versus time graph is linear, I know it's first order. And if it's the 1/over concentration versus time graph, then I know it's second order. Okay? But in any case, only one of those has come out to be linear, and that's a way to indicate what the order is. Okay? Another graph that this shows, which is different, is related to this, that when a zero order reaction happens, the rate of the reaction is constant until all the reactant is gone, and then all of a sudden the reaction stops. So this would be a graph that's unique to a zero order reaction. All right, so what does a zero order rate law look like? So it's a reaction that's independent of the concentration. So adding the reactant doesn't speed it up or slow it down. The rate law, the rate is constant. So the rate equals K. K is my rate constant. And if you had the reactant A to the 0 power, because it's zero order, well, any number that I plug in for A, if I raise it to the 0 power, it becomes a 1. So 1 times K, basically the concentration of the reactant is irrelevant. It doesn't have to be included. So what units would K have? Think about it for a second. But I know rate is always molar per second. If the only thing on the other side is K, then K has to have the units of molar per second also. So the units of rate and K would be the same in this case. All right, so this slide kind of gives a summary of a bunch of the stuff that we've done. Essentially, the first row tells me what the rate law looks like for zero order, first order, second order. Beneath, I have the equations that we learned. Now, for first order, this equation looks a little different. Again, it's using log rules, the integrated rate law. This is a different form of it. Don't worry about it too much other than make sure you learn one of the forms at least and be able to recall it and write it down on the test and solve problems. But then the zero order and the second order are here. If a problem specifies the order and tells you to work out the math, you just have to pick the right equation. Okay? This row here is about the graphs. When I make the three graphs, which I'm going to demonstrate in a minute, you can do concentration versus time, ln of concentration versus time, or 1 over concentration versus time. Those are the three graphs, and only one of them will be linear for whatever problem that you're doing. Okay? An additional thing that I haven't mentioned yet is that when you do the three graphs, whichever one is linear, the slope of that graph will give you the rate constant. Okay, now, if the slope of the graph is going up, that's a positive slope, which is what will happen in the second order reaction, then the slope equals K directly. On the other two, if they're linear, the slope of the graph is actually going to go down, which means it'll be a negative value, but we can change that to positive. Okay, so the slope of zero order and first order, if they're linear, it'll be the negative value of K. And then finally, half-life. I really don't like these three equations. I only like this one. Okay, the first order half-life is a constant value. It's a useful number to know. Like when we get into radioactivity, the half-life of carbon-14 is 5,730 years. That number never changes because it doesn't depend on the concentration of the reactant. Okay? Now, the half-life of a zero-order reaction actually changes like over time during a reaction. When the concentration of the reactant changes, the half-life changes. So the half-life is always changing, so really there's no point in finding it. Why would you want to find a value if 2 seconds later it's changed? Okay? Same thing on second order. Again, the concentration is part of the equation. So I don't see any point in knowing the half-life equations for zero order or for second order. There's no point. Just learn the one for first order. That's the one that actually is relevant. It'll come up in a bunch of problems that you have to do. So finally, some semesters we will assign the take-home quiz. You just have to talk to your professor in class and see if that's going to be assigned, or look for an email or something like that to instruct you. I'm going to talk a little bit through the graphs of it just to kind of get you started. So whether it's in D2L or in the shared class files, there are 2 files associated with the take-home quiz. The first one is a Word document. It says kinetics take-home quiz. It's going to tell us what the problems are that we have to solve. And then the second file is the kinetics data Excel spreadsheet. All right, so you need both of these files to work the quiz. So when we look at the quiz, again, this may change, but the first problem, actually the first couple of problems are things that we have talked about earlier in this PowerPoint. But I'm going to go to problem number 3. That's the first one where you probably need some assistance. So basically, number 3, it refers to a problem, the gas phase dimerization of butadiene. They studied this reaction at a temperature of 500 degrees. They collected data, which was concentration versus time data, and the data is all in the spreadsheet. Okay? And our job is to take that data. We're going to build the 3 graphs that we've described earlier to see, is the reaction zero order, first order, or second order? We're going to do that by building our graphs. Okay? You have to do that process for number 3, number 4, and number 5. They're 3 separate problems. So to do that, you're going to have to build 9 graphs. But the nice thing is, once we work the first problem and we get everything set up, then we can actually just switch the numbers for number 4 and 5. And if you switch it the right way, then the graphs and everything already be built. Okay? So that we're going to kind of simplify that process. So I'm going to go to the spreadsheet, kinetics data. Now, the spreadsheet, basically the way it's set up, the data's in the corner there. There are 3 problems. It's problem 3, 4, and 5 from the Word document that are here. Each problem is a separate tab. There's problem 3, problem 4, and problem 5 on the tabs, okay? And then each problem, the way this spreadsheet was set up, since this is a quiz that we expect people to do, the numbers in the spreadsheet are randomized for every student. So every student is going to get a different set of numbers, and actually it's set up so that every time you do something to the numbers, it's going to change them. So the first thing you have to do if you're going to use this data is you're going to have to copy that data, open up a new spreadsheet, and paste it in. So I copied it, open up a new spreadsheet, and I'm going to right click, and I'm only going to choose, there's several pasting options. I'm going to choose the pasting option that says paste values. Okay, one of the options says paste values. And basically, the previous spreadsheet had an equation it was using to calculate the numbers. We want to get rid of the equation. We just want the values of the numbers to be pasted in, and that way they won't change anymore. If you don't do this step, then it's going to mess you up. So, we have in our graph, and let me blow it up a little bit. So in our graph, in our data, the first column is the time. So we have an experiment that over time we measured the amount of the reactant that was still in the container. So on the first column, it's all the time values. In the second column, they're the concentration values. Now if you remember the 3 graphs we have to make concentration versus time. That's using the 2 columns that we have. So the first graph, we already have everything. But then I'm going to do the natural log of the concentration values versus time for the second graph. And then I'm going to do 1 over the concentration values for the third graph. So I need to set up all my data columns to give me the numbers that I need. All right? So as I said, column A is time. Column B is concentration. So I'm going to go to column C, and I'm going to type in at the top for a header, natural log of concentration. Okay, so column C, I'm going to take all my concentration numbers, do the natural log of them, and put them into that third column. Now, I don't want to do that by hand. It's a real pain to have to do, there's 20 different data points there, or more than that. I don't want to have to do each one of those by hand with a calculator. I want Excel to do it for me. So, again, I'll blow it up a little bit more. So I'm basically going to go to the first box by the concentration value. So here's my first data point. I'm going to the box right beside it, and I'm going to type in an equation for Excel to use. Okay, so I'm going to type in equals ln, which by the way, if you don't know a formula, Excel does have a bunch of standard formulas that if you hit the FX right beside the box that I'm typing in, you can find the natural log formula. Okay, it'll do averages and standard deviations and all kinds of stuff for you. But it's the ln, and I'm going to do parentheses. Okay, so I want to take the natural log of the box that's right beside it. That's column B, box 4. So I'm going to take the natural log of the number in box B4. So I type B4, close my parentheses. So I did equals ln parentheses B4 close parentheses. That's the equation. Now I just hit enter. And it calculated the natural log of the number right beside it. Now, I don't want to have to type the equation over and over again. So I'm going to now click back on that box. In the bottom right corner of the box, there's a little square right there. If I grab that and drag it down, it'll apply that formula to the whole column. So I click on the corner, drag it down, and it calculates all the numbers I need for the natural log of concentration values. All right, so then I'm going to go to column D. This time I'm going to type in the top 1 over concentration. So again, that's just my title. So this column is going to be 1 over concentration values, the first box. Again, I'm going back to concentration, which was box B4. I'm going to put equals. I'm going to do 1 divided by B4. This box equals 1 over B4. If I hit enter, it calculates the inverse or the reciprocal of the number that was in box B4. Once again, I just go back in my box, click on the bottom right corner, drag it down, and now I have all the data I need to make my graphs. So the first graph is going to be column B versus column A. That's concentration versus time. I need to make that graph right here. Then I can do column C versus A. That's natural log of concentration versus time. I can make that graph like right here. And then I can make column D versus column A, which is the 1 over concentration versus time. I can make that graph over here. Okay, so I can get all those graphs set up. I can look at them, and I might be able to eyeball and see which ones are linear, which one is linear and which ones aren't linear. Or if I can't tell, I could do linear fit on all 3 of them. And basically the one that is, because if it's experimental data, the chances are none of them are going to be perfect. But one of them should be closer to a linear relationship than the other 2. I could figure that out by looking at the R-squared values. Okay, so the one that is closest to linear will tell you the order of the reaction. All right, now, I'm going to assume that you guys know how to make a graph and refer to your data, so you can play with that if you need to. If you need help, you need to come talk to a professor or go to the ACT Center for help. Okay, but once I build those graphs and I pick out what order it is for problem number 3, I can actually go back to the other spreadsheet, click on the tab at the bottom to switch it to problem 4, copy the data, and if I come back to this one, which has all my graphs and everything on it, if you just take the data and paste it over the first 2 columns, it will still do the same calculations to get the other 2 columns, and it'll update all the data in the graph immediately, so that for problem number 4 and problem number 5, all you really have to do is just change the data in the first 2 columns. Also, this semester, when you do your lab related to kinetics, you're going to have to make these graphs with your data from lab. Once again, if you just take these graphs, copy in the data that you have, you may have to make a few little adjustments based on which experiment you're doing. But the setup for the spreadsheet, once you have kind of the template laid out for how all the data columns are calculated from each other and how the graphs pull data from those columns, once that's all set up, you don't have to build it anymore. You get one good spreadsheet, and then you can just adjust it each time you work a new problem. Okay? That's it for this PowerPoint. We are next going to chapter 21.